In the beginning of robot analysis, we have mentioned that we're actually answering two questions for robotic analysis. The first question, which we already covered that in the forward kinematics, is that at every joint, we already know the joint variable, all the theta, all the rotation, and all the translational motion of the prismatic joint. What is the final position and orientation of my end effector, which is the tool? The second question is, in the real task, we already know what is the desired orientation and position of my tool. Then what should be the theta and the prismatic displacement? What are all the joint variables we need to give so that we can achieve the final tooling position and orientation? So for example, in the industrial robotic collaboration, and there are a few robotic arms, and each arm has its own tooling. So for example, some of the robotic arm, it may be used like a grasper, and the other may be used like the welding, okay? And then the question is, at every time point, we have to be very careful to control the final position and orientation of the tooling. Then what should be the theta and the D we gave to the linear actuator or to the motor so that we can have a very well controlled robotic motion? So to answer the second question, we need to do the inverse kinematics. Okay, so the inverse kinematics, mathematically, it means that we already gave the position and orientation of the end effector. And what are the joint variables? Okay, so for example, here the H, this H, it means Tn0. Okay, Tn0 is the tool's frame, which is n in the world coordinates. Okay, so Tn0, we gave this real number matrix of the Tn0, and which in this case is H, and this is a 16 element matrix, and all are real numbers. And the question is, find one or all the solutions, and so that we know all the Q1 to Qn. Okay, so this means we need to, this Q means is either theta I for revolute joint or Di for revolute joint or Di for prismatic joint. Okay, so then it becomes a mathematical problem, right? And let's use one example to show that, what we're actually doing here. So now in the forward kinematic problem, we did one example, which was the Stanford manipulator. In the Stanford manipulator, we knew there were six joints, and 3 were RRP, and then we had a spherical wrist for this Stanford manipulator, which is the example 4. Okay, so if you cannot remember that, then please go back to the forward kinematics problems and then take a look at this this Stanford manipulator. So now for inverse kinematics, it means that, okay, so here we already have the Stanford manipulator, and for the Stanford manipulator, I want to control that so that I have the end tooling, which is my Tn0, and it needs to be this real number matrix. Okay, and this real number matrix is calculated from the real task, for example, from the real task. Okay, and then the question is, what should be the six joint variables? Okay, and if we know the 6 joint variables so that we can achieve this desired orientation and position, and we're all set, means we're able to use Arduino to control these 6 joints, either motors or linear actuators. Okay, and we also know that D2 and D6, they're given geometry, which is the geometry of the real manipulator link. Okay, and to solve that, And from the Stanford manipulator example, we have solved a Tn0. And remember that Tn0, you have a pretty complicated matrix. And here we have 0, 0, 0, 1. And each of these elements was a pretty complicated term that was a function of theta 1, theta 2, d3, theta 4, theta 5, and theta 6, right? And so now if we want to solve that, let's recall what we did. Okay, so we have solved these terms, which is R11. Here, this one is R11 and R12 and R13. So each of these terms is written by the joint variables. Okay, so now the question becomes pretty simple. That, okay, so this is the position and orientation we want to achieve. And we already know that based on the DH convention method, we already know that, okay, so the Tn0 matrix is a function of the 6 joint variables. And so it becomes pretty clear that these 12 elements are exactly equals to these 12 numbers, which is given as the desired rotation matrix. Okay, so it's clear. This is my calculated R11 from the forward kinematics by DH convention, and this term equals to this R11, and this is R12, and this is R13, and this is R14. Okay, so means in total we have 12. We have 12 terms, and we already know these 12 numbers. So means in total we have these 12 equations. Once we're able to solve these 12 equations, and then in this case we have 12 equations and we have 6 unknowns. Okay, but the thing is, all of these C1 is cosine and S is sine, so all of these are highly nonlinear. So which means in some cases we cannot really have the final solutions. Okay, so from this example we can see that the idea of inverse kinematics is straightforward. We're just solving equations so that we can solve for the joint variables. So that's it. But the difficulty is we cannot really solve those 12 equations to get the 6 joint variables because it's so complicated mathematically. So we need to think about what we can do so that we can solve for these 6 variables. So that is the key thing, the goal of solving inverse kinematics problems. Okay. So the reason is that the inverse kinematics may not have solutions. Okay, obviously these are highly nonlinear. These equations are highly nonlinear, and it's highly likely that it may not have solutions. And these problems may not have unique solutions. So it means although we can solve it, but it may have a couple of solutions. And because of the highly nonlinearity of the equations, the problems are usually difficult to solve, and which is obvious, means we cannot really do hand calculation to solve those. Okay, and also we want the solution to be closed form, and in most cases we want it to be closed form. Okay, so it means when the questions are pretty complicated, and normally we can use numerical method to solve it, but in the robotic examples, we want to use the closed form because we want to do the real-time control. And so later we will talk about it in detail. Okay, so then that is the inverse kinematics. The question is how we're gonna have some simple method so that we can solve a lot of equations to solve for the unknowns. So the closed loop solution. So the closed-loop solutions are preferred in most cases in robotics. It is because that in the real robotic control, at every time point, we want to give the motor, we want to know what should be the required joint variables so that we can quickly give these joint variables to our Arduino, for example, so that it can quickly control those joints. Okay, so when we want it to be quick, means the numerical iterations, we cannot really use that because normally it takes time. Okay, so for example, if you use your MATLAB to solve for some matrices, and may say sometimes takes 1 minute. For robotic control, that is too slow. It cannot really achieve the real-time tasking. So that's why we need the closed-loop solutions. For closed-loop solutions, we need to think about some simplified method so that we do not really need to solve those 12 equations. Instead, we have some idea, some method to do it. So that is kinematic decoupling. Okay, so for kinematic decoupling, and from this wording, it shows that we're actually doing the decoupling of the robotic manipulator. So for example, for a 6 degree of freedom, DOF means degree of freedom manipulator with at the last 3 axes of wrist intersection at the wrist center, which we have seen these examples in the forward kinematic problems, means we have 6 joints, but the rest 3, they are intersect at the wrist center. So means the last component is a spherical wrist. So if this is the case, then the problem can be decoupled into 2 simple questions. These 2 questions are the inverse position kinematics and the inverse orientation kinematics. Okay, so for example, the 6 degree of freedom Stanford manipulator, which in the beginning of this lecture we mentioned that, okay, so it seems like we need to solve for the 6 variables. Okay, so for the Stanford manipulator, we had a spherical wrist at the end, in the end, okay? And in total, we have 6 joint variables. And if this is the question, then this question can be regarded as finding the configuration of the arm for the position of the wrist center and the orientation of the wrist. Okay, so instead of solving the 12 equations, now we're actually doing 2 sub-questions. One is to solve for the position of the spherical wrist center, and the second is to find the orientation of the wrist. Okay, so what does it mean? So why we can do it? So for the 6 degree of freedom elbow manipulator, with the last 3 axes intersect as the wrist center, and we define the spherical wrist center as OC, and if we are now, I guess we're familiar with the manipulator and think about what we did in the example. So the last 3, they intersected at one origin, and now we name this origin as OC. So then the problem statement becomes, okay, so my Tn0 is a function of all the joint variables. Okay, so my Tn0 equals to the H is the given desired orientation and position. So it means we have a matrix and it has 12 real numbers. It should be a 16 element matrix, which is 4 times 4 matrix, but the last row is 0, 0, 0, 1, so it means we have 12 elements. Okay, and so to solve this question, it can be decoupled to 2 questions. The first question is, these 9 elements equals to the orientation, the rotation matrix R60, and the R60 is also a function of the 6 joint variables. Okay, and this matrix equals to these 9 elements. And this, again, this is a real number, and this is a real number matrix, and this is 4 times 4, and this is 3 times 3. And then you can also, the second equation we have is the displacement, which is these 3 elements. Okay, and this O60, and again, that is a function of the 6 joint variables, and it equals to these 3 elements. Okay, so now instead of we have this 12 elements, now we can decouple this question to these 2 equations. Okay, and again, these O and R, their desired position and orientation of the wrist means they're the given value we want to achieve, which is the real numbers. So now the question becomes, we want to solve these 2 equations so that we can solve for the Q1 to Q6, and these are the 6 joint variables. Okay, so it could be theta I or Qi. It depends on whether it is a prismatic joint, di, sorry, or a revolute joint. Revolute joint is going to be theta I. Okay. So now let's take a look at this diagram, which we have seen that in the forward kinematics problems. Okay, so we use this one as an example. So let's see, what is OC? And OC is the spherical wrist center, so in this case is right here. And this is our OC. And O4 and O5, they will be at the spherical wrist center. Means O3, O4, and O5, actually they have the same, they're at the same position, and which is the spherical wrist center. And the motion of the final 3 joints about these axes will not change the position of OC. Okay, so imagine what is the real manipulator. It means we have this manipulator, and in the end we install a spherical wrist, which is 3 servo spherical wrist. Okay, so that is like one component. And then these 3 motors, they're already attached to each other. They can be considered as one part. Okay, so now we add this one part. To this manipulator so that we have this diagram. Okay, so if this is our manipulator, then the motion of the spherical wrist is not changed with the position of the OC. Okay, so that means the position of the OC, so where we install the spherical wrist, is determined by these 3, right? These 3 joints. Okay, it means the position of the spherical wrist center is a function of the first 3 joint variables. Means this position is not determined by these frames. Obviously, that is true because these three joints decide where is this OC, and then we install the spherical wrist to this OC. Okay, so from the physical implementation, we can imagine this is true. Okay. And then we can do a quick decoupling for this question. So assume that we name the R is the orientation of the end effector with respect to the base frame. Okay, so that is R60. Okay, this is R60, and this is a real number, which is the desired value we want. Okay, desired orientation, real numbers. Okay, and then we can do a analysis of where is this O, and the coordinate of the end effector is, which is right here, right? Okay, so this is my O, which is the origin of the frame N, and frame N is, in this case, is frame 6, so that is the coordinate to represent the geometry of the end effector. Okay, so this is O. If we do the calculation from the spherical wrist, and this O is actually moving, we just do a quick translational motion from the spherical wrist center, and then we do a translational motion so that we can move the O directly. And remember, when we did this example in the forward kinematics, this final frame of the end effector is parallel to frame 5. Okay, so when we did the 4-parameter analysis. Okay, so here we have the x6, y6, and z6. Then if we consider the O from the spherical wrist center, and then we can quickly have this O that is the OC, which is this spherical wrist center with regard to the world coordinates, which is the base. Okay, so now we have the base. The base is right here, and we name that as the x0, y0, and z0. Okay, so this is my base, which is not movable. It's fixed, and it is corresponding to the real world coordinates. Okay, and my OC0 means where is my OC in this world space? Okay, so where is it? Okay, so if we want to calculate this O, because this O is just a motion from the spherical wrist to here, and we just do a translational motion of D6. So then we can calculate this O. The O is this OC. Then we do a translational motion. And this translational motion can be calculated by the orientation, which is R60, means this vector, this translational motion vector, times multiply the orientation matrix to with regard to the ground, which is the base. Okay, so that is actually R60 times 00 D6, right? 00 D6 is this vector. So we're actually considering this vector in the world coordinates. So that's why we need to times this R60. We have talked about it in the first lecture of transformation. Okay, and this means this part is equals to this part. Okay, and so we can do a quick analysis of the origins, the position of the origin of the end effector. And this effector, this position can be calculated by the position of the spherical wrist center plus this translational motion of D6, because there's no orientation between the frame 5 and the frame 6. It's just a motion. Okay, so now this equation is clear. Then we can do some calculation. Okay, and now what I would like to do is I move this part to the right hand side, so then I have this equation. So it means my OC0, which is the position of the spherical wrist center, equals to this O's position minus this vector, translational motion vector, times the rotation matrix, which is R60. And again, this R60 is the desired orientation, which we already gave from the final rotation matrix, homogeneous transformation matrix H. Okay, and this R is these 9 elements, which are real numbers. Okay, and then what is this OC0? OC0, obviously, it means the position of the spherical wrist center in the base, and here is my base. And so we can quickly use the XC, YC, and ZC, which means the coordinates of this point in the world coordinates, okay? So this vector equals to this O, and again, the O is the position, the desired position of my end effector, okay? So which is these 3 values, right? And which is we write it as OX, OY, and OZ, and they're real numbers. We're able to calculate T30, right? T30 equals to A1 times A2 times A3, and these three matrices, we're able to find the 4 parameters for each transformation. So finally, we have this T30 equals to a function of the 3 joints, which are theta 1, theta 2, and D3. And now we already know these three coordinates, means we know the vector of this T30, and we can do the decoupling so that it means from the O30 that is also a function of theta 1, theta 2, and D3. So then we can quickly find out what are the three variables. And then with these three variables, and we know that over R30 is also a function of these theta 1, theta 2, and D3. So then we can quickly find out the R30. Okay, so which is a function of theta 1, theta 2, and D3. Okay, so now by this decoupling, and we can find out this R30. So now the question is, okay, so we know the final orientation of the n-effector, and which is given. This R, and this is a real number matrix, and it is given, which is the desired orientation of the n-effector. And then we know this R30 from the kinematic decoupling, which we just calculated. So now the question is, we need to find this R63. And this R63, it means the orientation of the n-effector with respect to the spherical wrist center, which is right here. Okay, so the R63 can be calculated from these two known matrices, and this is a real number matrix, and this is calculated from the joint variable of the first three joints, so that R36 is the inverse of R30, and multiply R. Okay? So